Welcome to Grandpa's Late Nights. Come in, kiddo. Pull the blanket up a little higher, the way you like it. The corner tucked under your chin. There's no rush tonight. There's never any rush here. Wherever you are right now, in whatever corner of the world you've curled yourself into, I want you to know you've made it to the quiet part of the day. The part where nothing is owed and nothing is due. And the only thing left to do is let your shoulders come down from around your ears. So let them. Go ahead, just let them drop. I've got the porch light on, like always. The kettle's gone cold, but that's fine. I'll warm it again if either of us wants it. And the old chair is doing that little creak it does when I lean back in it. You know the one. Outside it's that deep kind of dark where the streetlights hum and the houses have all gone to sleep one by one, their windows winking out until it feels like the whole street is breathing slow and even, in and out, the way you're going to be breathing in just a little while. Before we begin, just a small thing, and I'll only say it the once, so it doesn't get in the way of the quiet. If these slow nights help you drift off, if you'd like a few more of them waiting for you whenever the lights won't switch off in your head, a little tap on that like button and a subscribe. It does help this sleepy little channel keep going. Small creators like me, we really do lean on it. And to those of you who've already settled in, who come back night after night and let this old voice walk you down into sleep, well, thank you. Truly, you've no idea what it means. So tell me, before you fade, where in the world are you listening from tonight? What time is it in your corner of the dark? Leave it down below if you're still awake enough to type, and if you're not, that's perfectly all right too. The words will still be here when you wake.
Now, I'll tell you the same thing I always tell you because it matters more than any fact I'm about to hand you. You do not have to follow every word of this. You don't have to understand all of it, or even most of it, or honestly, any of it. If you drift off somewhere in the middle, if you go under before I've gotten to the good part, that is exactly what's meant to happen. That's a win. The ideas will still be here. They're patient.
They've been patient for 100 years already, so they can wait a few more hours for you. All I want is for you to lie there and let the words wash over you like a warm bath that someone else is keeping the right temperature. So all you have to do is float. And I'll try, I really will try, not to make tonight's story so interesting that it keeps you awake. Though I'll be honest with you, kiddo, it's a good one. So if it does keep you up a little longer than you meant, well, at least you'll have learned something lovely on the way. A fair trade, I think, a fair trade. So here's where we're going tonight, slowly, gently, one little wonder at a time.
I want to tell you a secret about time. Not the time on the clock above the stove, not the time you keep meaning to go to bed at and never do. A deeper kind of time, the kind that lives underneath everything. Here it is. Right now, as you lie there, time is running faster at your head than it is at your feet.
I'll say that again, because it's the sort of thing that slides right off you the first time, the way a strange dream does in the morning. Time, the real underlying tick of the universe, is moving just a hair faster up where your head is resting than it is down where your feet are tucked under the blanket. Your head is, in the most literal sense, getting older a tiny bit quicker than your feet are. They are aging at different rates, the top of you and the bottom of you right now in your own bed. And before you wave that off as just one of those things people say to sound clever, the kind of thing that sounds poetic, but melts the moment you poke it, let me tell you that this is not a turn of phrase. It is not a metaphor. It is not me dressing up an idea to make it cozy. It is a measured fact. Somebody put a number on it. Somebody built the instruments and ran the experiment and watched it happen, and I want to walk you through exactly how, because the how is where the wonder really lives. Back in the year 2010 at a place called NIST, that's the National Institute of Standards and Technology, the people in the United States whose whole job, the entire reason they get up in the morning, is to measure things more precisely than anyone has ever measured them before. A small group of physicists set out to catch this effect in the act. Their names were Cho and Hume and Rosenband and Wineland, and I like to picture them in a quiet lab somewhere, the kind of room that hums with cold electronics, leaning over their machines the way you'd lean over a sleeping child, careful not to disturb a thing. What they had were 2 clocks, but not the kind of clock that hangs on a wall, and not even the kind on your wrist or your phone. These were atomic clocks, the most precise timekeepers that human beings have ever made. And the particular ones they used were optical clocks built around single ions of aluminum. Aluminum, the same ordinary metal as the foil in your kitchen drawer, except here, coaxed down to a single charged atom and made to keep time by counting the unimaginably fast shivering of light itself. Don't worry about the machinery of it. Just hold on to the picture. 2 clocks, so exquisitely, almost painfully accurate that they could measure differences in time finer than anything that had ever come before them. And here's the simple, almost childlike thing they did with these miraculous machines. They took 1 clock and they raised it up. Just a little, just 33 centimetres, that's about a foot, about the length of a school ruler, the kind with the metal edge that you'd run your thumb along. They lifted 1 clock up by roughly the height of a ruler above the other one, and then they sat back and they watched. And the higher clock, the one they'd lifted, began to run faster than the lower one. Measurably, provably. Just from being raised by the length of a ruler. Sit with that for a moment, kiddo, in the dark. 2 clocks in the same quiet room. One a hand's breadth higher than the other. And the high one ticking faster, getting ahead, pulling away into the future just a sliver quicker than its twin below. That is the whole of it right there. That is the thing happening between your head on the pillow and your feet at the end of the bed, except it's so small in your case that you'll never feel it. But it is there. It has always been there. And in 2010, 4 careful people finally held it still long enough to see it. Now, how big is this effect really? Because I can hear the sensible part of you, the part that's still half awake, asking the obvious question. If my head is aging faster than my feet, why am I not lopsided by now? Why isn't everyone walking around with an ancient head on young legs? And the answer is that the effect is faint, achingly, beautifully faint. Down here at the surface of the Earth, the rate at which time speeds up as you go higher works out to about 1 part in 10,000 million for every meter you climb. 1 part in 10 to the 16, the physicists would write it, which is just their shorthand for a 1 followed by 16 zeros underneath it. A number so enormous on the bottom that the difference on the top all but vanishes. For every meter higher you go, time speeds up by that almost nothing. So let's do the gentle arithmetic of a human life. If you spent your whole life, every minute of it, standing up, head held high, feet on the floor, instead of lying down flat the way you are now, then over a lifetime of 80 years or so, your head would pull ahead of your feet by maybe a few tens of billionths of a second, that's all. A few tens of billionths of a second of extra age, spread across 80 years, gathered up grain by the simple fact that your head spent its life a little higher than your toes. Utterly, completely imperceptible. You could never feel it. No clock you could buy at a shop could ever catch it. And yet, and this is the part I want you to carry down into your sleep, it is real. It happened. It's happening to you right now, in this bed. A fraction too small to imagine, but not too small to be true. Your head drifting just barely faster into tomorrow than your feet. Now, you might be lying there thinking, that's a sweet little thing, Grandpa. That's a lovely bit of cosmic trivia to fall asleep on. But what on earth does it have to do with me, with my actual life, with anything I touch in a day. And this is where I lean in a little closer, kiddo, because here is the part nobody tells you. That same faint effect, time running at different speeds, depending on how high up you are, is the reason the little blue dot on your phone knows where you are. It is the reason you can be dropped in a city you've never seen and still find your way to a warm bed. It is woven quietly, invisibly, into the most ordinary object you own. And if nobody had thought to account for it, your maps wouldn't be a little wrong. They'd be uselessly, hopelessly wrong. Let me put a picture on it so you feel the size of the thing. If the people who built the global positioning system, GPS, the satellites that whisper down to your phone, if they had simply ignored this business of time, running at different speeds up where the satellites are, then your phone's map wouldn't drift a few feet off. By lunchtime the very same day, your little dot would have wandered clean into the wrong town, and give it a couple of weeks of being ignored, and your phone would be confidently, cheerfully telling you that you were standing on the wrong continent, from a tiny difference in the speed of time. That's the stakes here. That's how close the strange and the everyday actually sit to one another. You've been holding a relativity machine in your pocket this whole time and never knew it. So how does that even work? How does a difference in the speed of time turn into your dot being in the wrong town? To understand that, and we'll go slow, there's no hurry at all. You have to understand one thing about how GPS really works, and it's not what most people think. Here's what most folks imagine. They picture the satellites somehow looking down, like eyes in the sky, seeing you, measuring how far away you are, drawing little lines down to your rooftop. As if the whole system is built on distance, on measuring how far. But that's not it at all, not even close. GPS is not a distance machine. Underneath everything, GPS is a clock. It is a timing machine. It works entirely from top to bottom by measuring time. And the distance only comes out at the very end, almost as an afterthought. Let me show you how, because once you see it, you'll never look at that little blue dot the same way again. Up there, far above you, are these satellites, and each one carries inside it an atomic clock, the same exquisite kind of timekeeper we were just talking about, the rubidium and cesium clocks, accurate to billionths of a second. And what does each satellite do ceaselessly day and night as it sails over your head? It does two simple things. It broadcasts over and over a little message that says, in effect, here is the exact time on my clock right now down to the billionth of a second, and here is exactly where I am up here in my orbit. That's it, the time on my clock and my position, said again and again and again, falling down through the dark to whoever's listening.
And your phone is listening. Your phone catches that message. And here is the clever, beautiful trick at the heart of the whole thing. Your phone looks at the time stamped on the message, at the time the satellite said it was when it sent the signal, and it compares that to the time the signal actually arrived. And from that it knows how long the signal was traveling, how long it took to fall from the satellite down to you.
Now that signal isn't traveling at any ordinary speed. It's a radio signal, which means it travels at the speed of light. And the speed of light is a fixed, dependable number, about 299,792,458 meters every single second. That's roughly 300,000 kilometers every second, fast enough to circle the whole Earth 7 times while you draw a single breath. And crucially, it's always the same. It never speeds up or slows down. It is the most reliable thing in the universe. So your phone has the time the signal took, and it has the speed the signal travels. And from those two, it can work out the distance. Time multiplied by speed gives you distance. The same way if I told you you'd been driving for 2 hours at 60 miles an hour, you'd know you'd gone 120 miles without ever looking out the window. Your phone does exactly that. It takes the travel time, multiplies it by the speed of light, and out pops the distance to that one satellite. But knowing your distance to one satellite isn't enough to find you. It just tells you you're somewhere on a great invisible sphere that far from that one satellite could be anywhere on it. So your phone listens to another satellite and another, at least 4 of them, usually more. And each one tells your phone how far away that satellite is and where it sits in the sky. And when you have 4 of these distances from 4 known positions, there's only one single point in all the world where all of them can be true at once. One place, and that place is you. That's where you're lying right now. That clever crossing of distances has a name. It's called trilateration. And it's the same idea, really, as figuring out where you are by how far you stand from 4 lighthouses you can see. So do you feel the shape of it now? The whole thing, the entire miracle of knowing where you are anywhere on Earth, rests on time, on measuring, with almost unbelievable precision, how long a signal took to arrive. The distance is just the time wearing a different coat.
And that, kiddo, is why this is so delicate. So heart-stoppingly delicate. Because if the timing is even a sliver off, the position is wrong. Let me give you the number that makes this real, and then I'll let you start to drift. Light travels so fast that in just 1 billionth of a second, 1 nanosecond, the briefest flicker of time a human mind can barely even name, light moves about 30 centimetres, about a foot. So a timing error of 1 single nanosecond, 1 billionth of a second of slop in the clocks, turns straight into a foot of error in where your phone thinks you are. 1 nanosecond, 1 foot, 2 nanoseconds, 2 feet.
The timing and the position are chained together, link for link, and the chain is the speed of light. Which means these clocks can't be a little bit off. They can't be off by a millionth of a second, which would already be 1,000 nanosecond, already hundreds of meters of error. They have to agree, the clock in the sky and the clock in your pocket, down to the billionth of a second, all day, every day, forever. The whole system lives or dies on that agreement. And now you can perhaps feel the trouble coming the way you can feel a storm before it arrives. Because we already know, we proved it, with 2 little clocks and a ruler's height of separation, that time does not run at the same speed up high as it does down low. We know that a clock lifted up runs faster than a clock left below, and the satellites carrying these precious atomic clocks are not lifted up by the height of a ruler. They are lifted up thousands and thousands of kilometres far above your head, out into the deep quiet above the weather. If a clock runs measurably faster when you raise it 1 foot, what in the world happens to a clock you raise 20,000 kilometres? That's the thread we're going to pull tomorrow's part of the way down this story. But let me set one more thing in your mind first, softly, like laying out clothes for the morning. Because there's a belief, a comfortable little belief, that most people carry around without ever questioning it. The belief is this, that all of this relativity business, this stuff about time bending and stretching and running faster up high, is just theory, just clever ideas on a chalkboard, just thought experiments dreamed up by a wild-haired man 100 years ago, the kind of thing that matters to professors and to no one else. Interesting, sure. Strange, certainly. But real in your daily life, in your kitchen, in your car, in your hand. Surely not. Surely that's all far away in the realm of black holes and rocket ships and things that have nothing to do with you. That belief feels so reasonable, so settled, so obviously comfortably true, and it is completely, beautifully wrong. It's wrong in a way that's hiding in plain sight, running quietly in the background of the most ordinary moment of your day, every time you glance down at a map to find your way home. The wild-haired man was not just right in the abstract, he was right in a way that engineers had to build around, had to wrestle with, had to design clever little fixes for, or the whole thing would have fallen apart before it ever began. There were even, and I'll just leave you this thread to hold as you start to sink, there were even scientists, real ones, who weren't entirely sure it was real, who looked at the prediction that the satellite clocks would run faster and thought maybe not, let's wait and see. And so they did something about that doubt, something rather wonderful, something I'll tell you all about when we pick this up again. They built in a way to test it, to turn the strangeness on and off and see for themselves. But that's for the next part of the night. For now, just hold the two pictures side by side as you breathe. The little clock lifted a ruler's height, ticking faster than its twin, and the satellites lifted thousands of kilometers higher, sailing silently over your sleeping house. Somewhere between those two pictures lies the reason you can always find your way home. And somewhere in there, too, is the quiet proof that the strangest ideas about the universe aren't far away at all. They're right here, in your pocket, over your bed, running faster at your head than at your feet this very moment, while the porch light glows and the street breathes slow and you, kiddo, drift gently down toward the place where none of it needs explaining. We'll keep going in just a moment. There's no hurry, there never is. So, where were we? The clock at your head, the clock at your feet, and that thread of doubt I left you holding. Let me pick it up gently, and let me start with the prize, the thing that gives this whole long night its name. Time runs faster at your head than at your feet. I know how that sounds. It sounds like something a tired grandfather makes up to keep a child quiet. But it's true, and what's more, somebody measured it, and they didn't have to climb a mountain or fly to the stars to do it. They did it across a distance smaller than the length of your forearm. The year was 2010. A handful of physicists at a place called NIST, the National Institute of Standards and Technology, set out to catch time in the act. Their names were Chu and Hume and Rosenband and Wineland, and I say them out loud the way you might say the names of old friends, because they did something quietly astonishing. They took two clocks, not the clocks on your wall, not even the clocks in your phone. These were optical clocks built around single ions of aluminum, ticking so impossibly fast and so impossibly steady that they could split a single second into pieces almost too small to imagine. And then they did the simplest thing in the world. They lifted one of the clocks, just a little, just 33 centimetres higher than the other, about 1 foot, about the height you'd raise a glass of water from the table to your lips. And the higher clock ran faster, measurably, provably. Not by much, mind you, not by anything you could ever feel or see or notice in a lifetime of noticing. But there it was, written in the numbers, plain as anything. The clock that sat a little higher in the world ticked a little quicker than its twin below. And the difference came down to this. At the surface of our Earth, time speeds up by about 1 part in 10,000 trillion for every meter you climb. 1 part in 10 to the 16th power, if you like the language of it. A number with so many zeros it stops meaning anything to the ordinary mind. So small that if you stood upright for 80 years instead of lying flat, your head would age ahead of your feet by only a few tens of billionths of a second across your entire life. Nothing and everything, because it's real. Because someone caught it happening across a foot of empty air. So that's the strange little seed of it. And you can carry it down into sleep just as it is. Your head, this very moment, resting a touch higher than your feet there beneath the blanket. is moving through time, just a hair faster than the rest of you. You are, in the gentlest and most useless way imaginable, slightly out of step with yourself. And it's fine, it harms nothing. It's just the universe being exactly as odd as it always quietly was. Now, here is where the oddness stops being a curiosity and starts being something you lean on every single day without ever once thinking about it. Because that same effect, that same speeding up of clocks lifted higher into the sky, doesn't stay polite and tiny forever. Lift a clock not 1 foot, but 20,000 kilometres, and the little difference grows teeth. Let me tell you what would happen if nobody had ever thought about this. If the engineers who built the thing in your pocket had simply shrugged and said, "Relativity, that's for professors, that's not for us." Picture it. You wake, you reach for your phone, you open the little map to find your way somewhere new. And the blue dot that's meant to be you, the dot that always sits so faithfully right where you're standing, would be wrong. Not by a step. Not by a street. By the time the morning was over, by lunchtime, that dot would have wandered off into the wrong town entirely. And if you left it uncorrected day after day, the error would pile up and pile up the same direction every time, never cancelling, never resting, until within a couple of weeks the map would be placing you on the wrong continent, you lying right here in your own bed, and the machine insisting with perfect confidence that you were somewhere across an ocean. That's not a guess, that's the arithmetic. And to understand why such a small thing in the sky becomes such an enormous thing on the ground, you have to understand one fact that almost nobody is ever told. And it's the kind of fact that, once you have it, changes how you think about that little dot forever. Here it is. Your GPS does not measure distance. It never measures distance. Not directly, not once. What it measures is time. Sit with that a moment, because it runs against everything the name suggests. You'd think a positioning system would somehow reach out and measure how far away things are, the way you might pace out a room. It does no such thing. Up there, in what's called medium Earth orbit, some 20,200 kilometers above your head, a small fleet of satellites is sailing in great slow circles around the world, and each one is doing something beautifully simple. It is shouting over and over into the dark, not words, two things only: the time right now by my own clock. And here, right now, is where I am in my orbit. That's the whole message, the time and the place, sent down on a radio signal that races toward you at the speed of light. And the speed of light, kiddo, is not infinite, though it's close enough to fool anybody. It travels at about 299,792,458 meters every second. A number worth saying slowly, because it is one of the truest numbers there is. Light does not hurry for anyone. It crosses the room before you can blink, yes. But it does take time, and that little bit of time is the whole secret, because when that signal finally reaches the chip in your phone does something clever. It looks at the time stamped on the message, the moment the satellite said it left, and it compares that to the moment it arrived. The difference, that tiny sliver of delay, tells your phone how long the signal was traveling. And once you know how long light traveled, you simply multiply by the speed of light, and out falls a distance, how far away that one satellite is. Then it does the same with a second satellite, and a third, and a fourth. And where all those distances agree, where all those invisible spheres of light overlap on a single point, that point is you. Your blue dot. They call it trilateration, that crossing of distances, but you needn't remember the word. Just remember the heart of it. The whole machine is a clock-comparing machine. It finds you in space by measuring time, nothing else. And now you can feel, I think, why a clock that's even a little bit wrong becomes a catastrophe, because if the timing is the foundation, then any crack in the timing brings the whole house down.
Light moves so fast that a mistake of even a single nanosecond, 1/1000th of 1 second, that absurd, unfeelable flicker, translates into about 30 centimetres of error in where it thinks you are. 1/1000th of a second, a foot of confusion. So you can see what's coming. If those satellite clocks were drifting ahead by the kind of amounts relativity insists upon, amounts thousands upon thousands of times larger than a single nanosecond, then the foundation isn't cracked. It's gone.
The blue dot doesn't wander, it runs. So that, my dear, is the trap the universe lays for anyone who wants to build a machine like this. You need clocks in the sky and clocks on the ground to agree perfectly, down to the billionth of a second, forever. And the universe simply will not let them. It speeds the high clocks up. It is not a bug, not a flaw in the equipment, not something better engineering could ever fix. It is woven into the shape of space and time themselves. The clocks up there will run fast because they are up there. That is just the rule of the place we live in. And here, just here, is where I want to set down the last thought before we drift on, because it's the one that most people get exactly backwards. There's an old comfortable idea, and maybe you've held it yourself, that relativity is just theory, just a notion. Something clever men chalk onto blackboards in rooms you'll never enter, true perhaps in some far cold corner of the cosmos, near a black hole maybe, near the speed of light maybe, but surely nothing to do with you. Nothing to do with a warm bed and a phone on the nightstand and a quiet street outside. Surely the real world, your world, runs on plain old common sense, and the strange stuff stays safely out among the stars. It's a lovely idea, and it is completely, provably wrong. That's the thing I want you to carry down into the deep part of the night, the wrongness of it, because everything I'm about to tell you, every fix and switch and clever offset the engineers dreamed up, only exists because relativity is not a theory in the dusty sense at all. It's a daily chore, a line of arithmetic that has to be done and done right, billions upon billions of times every day, in every pocket, in every car, on every plane, or else the world's most used machine simply stops working by lunchtime. But we'll get to all of that slowly. There's no hurry, there never is. So let's start with the first of the two, because understanding them separately is the only way to see why they don't cancel. The first effect comes from Einstein's special relativity. Published in 1905, when Einstein was 26 years old and working as a patent clerk in Bern, special relativity began not with satellites or clocks or any practical concern whatsoever. It began with a question so pure and simple that it hardly sounds like physics at all. What happens, Einstein asked, if you actually keep up with a beam of light? What do you see? He'd been turning the question over since he was 16, walking home from school, imagining himself running alongside a wave of light the way you might run alongside a friend. And the answer, when he finally worked it out, was quietly catastrophic for everything Newton had built. The answer was, you can't. Not because you're not fast enough, though you aren't, but because the universe is arranged so that light always moves at the same speed relative to any observer, no matter what. The speed of light is not measured against the ether or against some fixed backdrop. It is measured against you, wherever you are, however you are moving, always the same. About 299,592,458 meters per second, every time. And that constancy is the source of all the strangeness that follows. Because if light always travels at the same speed, no matter how fast you are moving, then something else has to give. And what gives? What the universe quietly adjusts to keep the speed of light constant is time itself. Here's the simplest way to feel it. Imagine a clock made of light. Just a photon bouncing back and forth between two mirrors, ticking each time it reaches a mirror. Now imagine that clock is moving sideways, very fast. From where you stand watching it go by, the photon isn't just bouncing straight up and down, it's tracing a diagonal path, up and across, down and across, because the whole clock is sliding through space while the photon travels. The path the photon takes, from your perspective, is longer than the path it takes from the clock's own perspective, but the photon must travel at the same speed regardless. So if the path is longer and the speed is the same, the time between ticks must be longer. The moving clock from your viewpoint ticks more slowly. This is not an illusion. It is not a trick of perspective the way a train looks smaller when it's far away. It is a real, physical, measurable reduction in the rate at which time passes for a moving object relative to a stationary observer. Physicists call it velocity-time dilation, and it is not subtle when the speeds involved are high enough. Now, GPS satellites are not moving at the speed of light, not even close, but they are moving very fast. Each one travels at roughly 3.87 kilometers per second, which is about 14,000 kilometers per hour. That is about 12 times faster than a rifle bullet. It is fast enough for special relativity to leave a mark. And the mark it leaves is this: because the satellite is moving at 3.87 kilometers per second relative to you, standing or lying still on the surface of the Earth, its onboard clock appears to you to tick a little more slowly than yours. The effect is small. It works out to about 7.2 microseconds per day, 7.2 millionths of a second slipping away, the satellite's clock falling behind relative to ground-based time. Negative 7.2 microseconds. The satellite loses time because it is moving. That is the whole of special relativity's contribution to the GPS story. One number, one direction, one cause, but there is a second effect, and this one comes from somewhere else entirely. In 1905, Einstein gave the world special relativity, and it was extraordinary. But even as he published it, he knew it was incomplete. Special relativity only worked cleanly for observers who were not accelerating, not changing their speed or direction. As soon as you introduced gravity, which is not merely a force but a constant, pervasive acceleration, you needed something more. Einstein spent the next 10 years trying to find it, and the search led him somewhere he hadn't expected, somewhere deeper. By 1915, he had it. General relativity. And where special relativity had reshaped time through motion, general relativity went further and reshaped time through gravity itself. Here is the core of it, as gently as I can carry it. You probably think of gravity the way Newton described it, as a force, like a rope between heavy objects, tugging them toward each other across empty space. It's an intuitive picture, and Newton's equations still work beautifully for everyday purposes. But Einstein proposed something entirely different. He proposed that mass, the stuff that makes up planets and stars and your own body, actually bends the fabric of space and time together. The universe isn't a flat stage on which events play out. It's a flexible, curved thing, and mass deforms it the way a bowling ball deforms a stretched rubber sheet. Objects moving through space follow the curves that mass has made in it. They're not being pulled, they're following the landscape. That's the geometry part. But here's the piece that matters for our story tonight. Space-time doesn't just curve differently at different distances from a massive object. It also flows at different rates. Time itself runs at different speeds depending on how deep you are in a gravitational field. Deep in the well, close to a massive object where the curvature is strongest, time runs more slowly. High above the well, far from the mass, where space-time is less bent, time runs more quickly. Think of it like this. Imagine space-time as a river flowing. Near the surface of the Earth, near the heavy mass, the river runs sluggish, slow. Higher up, further from that weight, the river quickens. A clock near the Earth's surface is swimming in a slower current. A clock far above the Earth at the altitude where GPS satellites orbit is swimming in a faster current, and so it ticks faster. This is gravitational time dilation. And for GPS satellites orbiting at roughly 20,200 kilometers above the Earth's surface, about 26,560 kilometers from the planet's center, the effect is significant. At that altitude, the gravitational field is considerably weaker than on the ground. Space-time is less curved up there, and the satellite's clock, swimming in that thinner, faster-flowing stretch of time, gains about 45.9 microseconds per day relative to a clock on the ground below. Positive 45.9 microseconds. The satellite gains time because it is higher. That is the whole of general relativity's contribution to the GPS story. One number, one direction, one cause. So now we have both of them. Velocity time dilation from special relativity, the satellite moving at 14,000 kilometers per hour, pulls the clock backward minus 7.2 microseconds per day. Gravitational time dilation from general relativity, the satellite sitting high above in a shallower gravitational well, pushes the clock forward plus 45.9 microseconds per day. Two forces, two effects, both real, both acting on the same clock every second of every orbit. And now here is the moment where the comfortable misremembering tends to slip in, because when people hear this, two effects, one pushing up, one pushing down, the natural instinct is to exhale and say, oh, they cancel, how tidy, the universe sorted itself out and no one has to worry about it. But they don't cancel, not at GPS altitude, not even close. Minus 7.2 and plus 45.9 do not add up to 0. They add up to plus 38.7 microseconds. Every day, the satellite clock gets ahead of the ground clock by roughly 38 microseconds. The gravitational effect is more than 6 times larger than the velocity effect, and it wins completely and decisively, pulling the net result strongly in the positive direction. The satellite's clock runs fast. Not slightly fast, not ambiguously fast, but measurably, consistently, consequentially fast. The myth that they cancel is understandable. It has a kind of narrative satisfaction to it. The universe is elegant, people assume, and elegant things resolve neatly, but the universe is only as neat as the numbers allow, and the numbers here do not allow cancellation. They allow 38 microseconds of daily drift, and that is what we have to reckon with now. You might wonder, and it is a perfectly good thing to wonder, why the gravitational effect is so much larger at GPS altitude. Why does gravity win so completely over speed? And the answer comes down to where exactly these satellites are in relation to the Earth. GPS satellites fly in what is called medium Earth orbit, or MEO. 2,200 kilometers up is too close. 36,000 kilometers up, geostationary orbit, where weather satellites and TV satellites tend to sit, is much further away. GPS sits in between at that altitude of roughly 20,000 kilometers above the surface. From the planet's center, that's about 26,560 kilometers out. At that distance, the satellite is far enough from the Earth that the gravitational field has weakened considerably. And because it's so high, it needs to travel at a lower orbital velocity to maintain a stable orbit. That interplay between height and speed is just Kepler's law, the same mechanics Newton worked out 3 centuries ago. Higher orbit, slower speed. So these satellites are moving relatively less quickly than a low Earth orbit satellite would be, which damps the special relativistic effect. And they're sitting considerably higher in the gravitational well, which amplifies the general relativistic effect. Both things together mean that at GPS altitude, it is general relativity, the gravity side of Einstein's work, that dominates. But here is something rather beautiful and strange. There is an altitude at which the two effects are exactly equal and perfectly opposite, and they do cancel. That altitude is about 3,200 kilometers above the Earth's surface. Below that level, a satellite is moving fast enough and close enough to the Earth's gravity that the velocity time dilation wins and the satellite's clock runs slow. Above that level, the gravitational effect takes over and the clock runs fast. Exactly at 3,200 kilometers for a brief crossing, the two effects precisely balance. GPS satellites orbit at 20,200 kilometers. They are far above the cancellation point. They are firmly in the gravitational regime where space-time's slower flow close to Earth makes the satellite's clock, high above, run faster and faster with each passing day. 38 microseconds per day. It always comes back to that number. And I want to stay with it for a moment because the number by itself doesn't quite do justice to what it means for the machines we rely on. So let me translate it into something more concrete. The speed of light is roughly 299,792,458 meters per second. Another way to say that, a way that GPS engineers think about it more naturally, is that light travels approximately 30 centimeters in 1 nanosecond, 1/1000th of a second, about the length of a hand. That is the fundamental unit of GPS's error budget. 1 nanosecond equals about 30 centimeters of uncertainty in your position. Now 38 microseconds is not 1 nanosecond, it is 38,000 nanoseconds. 38,000 of those 30 centimeter increments accumulated in a single day. Multiply 38,000 by 30 centimeters and you do not get a small number. You get approximately 11,400 meters, 11 kilometers, roughly 11 to 12 kilometers of positional drift accumulating silently every day if no one does anything about it. And this is not the kind of error that bounces around randomly and averages out. It doesn't sometimes drift north and sometimes south so that over a week you're still roughly where you should be. It is monotonic. The satellite clock is always gaining, always running ahead, always fast. The drift goes in one direction only, accumulating relentlessly day after day. After one day, 10 kilometers wrong. After a week, 70 kilometers wrong. After a month, the navigation solution is not off by a city block, it's off by a country. And in 2 weeks' time, if you were relying purely on uncorrected GPS signals for navigation, you might well find yourself, at least according to your phone, somewhere in the middle of an ocean. So yes, the stakes are real. And that is why the fix was not optional, not approximate, not something the engineers thought about and decided to worry about later. The fix had to be there from the beginning, designed in, before any satellite was ever launched. But let's not get to the fix quite yet. Because before the fix, there is something I want to settle properly, which is this question of why the cancellation myth persists and what it tells us about the way we tend to think about physics. The myth comes, I think, from a reasonable instinct. When people learn that special relativity makes fast-moving clocks run slow and general relativity makes high-altitude clocks run fast, there is a tempting mental shortcut. The satellite is both fast and high. Maybe nature balanced the books, maybe it's self-correcting, maybe this is one of those beautiful coincidences where everything works out. And in a different universe with different constants it could have. If the Earth were more massive, or the GPS satellites moved faster, or they orbited at a different altitude, the balance might fall differently. In this universe, with these numbers, general relativity beats special relativity at every altitude above about 3,200 kilometers, and GPS satellites orbit at 20,200 kilometers. The cancellation altitude is nowhere near GPS altitude. The net drift is large and real and relentless. The other reason the myth persists, I suspect, is that we are not used to thinking about the two theories as separate things with separate equations and separate magnitudes. When people say Einstein's relativity, they tend to mean the whole edifice at once, a single idea, and a single idea feels like it should produce a single tidy answer. But special and general relativity are not one theory dressed up twice. They are different structures built on different foundations, describing different physical phenomena, and at GPS altitude they just happen to point in different directions with very different strengths. The universe did not consult our preference for tidiness. 38 microseconds, the two effects separated, honest about their sizes. That is the real number, and nothing about it cancels. Now, there is one more thing I want to say about where these two effects come from, because I think it deserves a moment of quiet attention before we move on to the engineering solution, because these are not obscure effects applying to exotic objects. They are acting right now on the most ordinary things imaginable. They are acting on you. At this moment, wherever you are lying down, whatever altitude you're at, whatever latitude, your head is further from the center of the Earth than your feet are. Not by 20,000 kilometers, by something much more intimate and much more immediate, by the length of your own body, perhaps 1.5 meters, perhaps a little more. And Einstein's equations don't have a minimum height. They apply everywhere, to every height difference, no matter how small. Which means your head, being very slightly higher in the Earth's gravitational well than your feet, is sitting in very slightly less curved space-time. It is swimming in a very slightly faster flowing stretch of time, and so it ages ever so slightly faster than your feet. The difference, over 1.5 meters of height, works out to roughly 1 part in 10 to the power of 16 per meter, which is an almost insultingly small number. Per meter of height, 1/10 quadrillionth faster. Over a human lifetime of 80 years, the total accumulated difference between the top of your head and the soles of your feet is on the order of a few tens of billionths of a second. You will not notice it. You cannot feel it. You will not live long enough for it to matter in any practical sense, but it is real, measurably, verifiably real. And I will tell you how we know that in just a moment, because the experiment that proved it is one of the most remarkable and quietly beautiful things physics has produced in recent years. First, though, I want to come back to the two effects one more time, because there is a detail buried in the GPS altitude numbers that I think rewards a moment's attention, and it has to do with the crossover. We said the two effects cancel at about 3,200 kilometers. That is not a magical number plucked from the air. It falls out of the mathematics when you set the special relativistic time dilation formula equal to the general relativistic one and solve for the orbital radius. The algebra is not especially complicated, though I'll spare you it tonight. What matters is the implication. Below 3,200 kilometers, satellites are in the speed-dominated regime. A satellite in very low Earth orbit, like those used for some spy imaging satellites or some recent commercial broadband constellations, is moving very fast and not very high. Its clock runs slow. The special relativistic effect wins. Above 3,200 kilometers, as you climb, the gravitational dominance grows. At GPS altitude 2,200 kilometers, gravity has completely run away with the result. The clock runs fast by 38 microseconds a day, and at exactly the crossover 3,200 kilometers, a hypothetical satellite would experience no net relativistic frequency shift at all. Its clock would tick at exactly the same rate as a clock on the ground, which sounds like a convenient thing, no correction needed, but nobody actually operates navigation satellites at 3,200 kilometers for reasons that have nothing to do with relativity and everything to do with radiation belts and orbital stability. The crossover is elegant in theory and irrelevant in practice. GPS lives at 2,200 kilometers, firmly in the regime where gravity tells time to hurry. And now, before we go further into what the engineers decided to do about it, and there is a quite remarkable story there, with a switch and a confirmation and a genuinely uncertain moment in the history of the whole enterprise, I want to circle back to something I mentioned at the start of all this, the most intimate version of the effect, the one that isn't about satellites at all. Because we've been talking about 2,200 kilometers and 38 microseconds, and the infrastructure of a global positioning system, and those are real and important numbers. But sometimes the right way to understand a thing is to make it very small. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, NIST, one of the most precise measurement institutions in the world, did something that might be the most quietly extraordinary experiment of the past few decades. Their names were Chu, Hume, Rosenband, and Wineland. And what they did, in essence, was put two clocks on a shelf, one slightly higher than the other, and watch one of them run faster. These were not ordinary clocks, they were optical atomic clocks using a single, trapped aluminum ion as their timekeeping element. An aluminum ion is an atom of aluminum that has had one of its electrons removed, giving it a slight electric charge so it can be held in place by electromagnetic fields. At the heart of these clocks, the ion vibrates at an extraordinary frequency in the optical range, which means it oscillates at roughly a quadrillion times per second. Frequencies that high allow for precision that was simply unimaginable a generation ago. These were the most accurate timekeepers ever built at the time they were used. The physicists measured the tick rates of two of these clocks, identical technology side by side, and then they raised one of them very slightly relative to the other, not 20,000 kilometers, not even 20 meters, 33 centimeters, about 13 inches, roughly the distance from your elbow to your wrist. At that height difference, the gravitational time dilation from Einstein's general relativity is utterly minute. 1 part in 10 to the power of 17, roughly. A number so small it strains language to describe it, but these clocks were precise enough to see it, and they did see it. The higher clock, sitting 1/3 of a meter closer to the ceiling and 1/3 of a meter further from the Earth's center, ran measurably, detectably faster than the lower one. The difference matched Einstein's prediction. That is the experiment, that is the measurement, and I think it deserves a moment of stillness, because what it means is this: the effect that GPS engineers account for with their frequency offsets and their orbital mechanics and their signed relativistic corrections is not merely a large-scale phenomenon that only emerges at satellite altitudes. It is happening everywhere, on every shelf, in every room, between your head and your feet. The gravitational time dilation that gives GPS satellites their 38 microseconds per day is the same physical effect, the same equation, the same universe, just applied to a much smaller height difference, and therefore producing a much smaller result. The effect scales with height. At 20,200 kilometers, it is large enough to wreck global navigation. At 33 centimeters, it is small enough to require the most precise instruments ever constructed to detect. But it is the same effect. Your head is living in slightly faster time than your feet, not metaphorically, physically. The experiment has been done, the number has been measured. Einstein's equation holds from the altitude of GPS satellites all the way down to the height of a forearm. It is an astonishing thing to carry into sleep. But I'm aware that we've been building towards something, and the question that might be sitting with you now, the one that feels almost too obvious to ask, the engineering question, is simply, what did they do about it? The satellite clocks run fast by 38 microseconds per day. The whole system falls apart without nanosecond level timing. 38 microseconds is 38,000 nanoseconds, and that turns into 11 or 12 kilometers of positional drift every single day. What did the engineers do? And the answer, when you hear it, is one of those moments where engineering and physics meet in a way that is almost playful, almost mischievous, because the fix is not a software patch uploaded to the satellites. It is not a correction algorithm running on a computer somewhere that adjusts the numbers after the fact. The fix is built into the atomic clock before it ever leaves the ground. Before launch, before the satellite is even assembled, the clock's frequency is set to run slightly slow, deliberately, precisely, calculatedly slow. The nominal frequency of the GPS atomic clock is 10.23 megahertz. That's the frequency it's supposed to tick at in orbit from the perspective of users on the ground. But on the ground, in the lab before launch, the clock is not set to 1023 MHz. It is set to 10.2999 Einstein 543 MHz, a tiny fraction less than it should be. A deliberate retardation of 4.465 parts in 10 to the 10th power. Let that number settle for a second. 10.22999999543 MHz. That is not a round number. That is not an approximation. That is a precisely calculated offset derived directly from Einstein's equations, chosen so that when the clock reaches orbit and gravity and velocity together push it forward by 38 microseconds per day, the pre-inserted slowness cancels the gain exactly, and the clock ticks at the right rate for the people below. The engineers looked at Einstein's equations and they did not argue with them. They did not look for a workaround. They trusted the mathematics enough to tune a physical clock to a specific non-round frequency, and they sent it into space, confident that the universe would do the rest. And it does, every day. There is something in that which I find quietly beautiful. The fix is passive. It doesn't require anything to happen. It doesn't require a signal from the ground or a running program on the satellite. The satellite simply rises into orbit, and as it rises, the universe, behaving exactly as Einstein said it would, accelerates the clock, and the pre-inserted retardation absorbs the acceleration, and the clock ticks at 1023 MHz as seen from the ground, just as it should. The correction is baked in, the physics does the work. But, and this is where the story gets interesting and where I want to leave you in just a moment, balanced on the edge of something. Not everyone was sure it would work. Not everyone was sure, in the 1970s, that the effect would actually appear as predicted. Not everyone was willing to trust Einstein's equations enough to pre-tune the clock and simply assume the universe would oblige. There was a faction, engineers and scientists, who felt that the relativistic effect on satellite clocks had never been directly confirmed in orbit. The Hafele-Keating experiment in 1971 had flown atomic clocks on airliners and seen both relativistic effects, and that was remarkable. But an airliner is not a satellite. The speeds are different, the altitudes are different, the conditions are different. Confirming the effect at airliner altitudes was not the same as confirming it at the altitudes and velocities where GPS needed it to be true. And so when the early navigation technology satellites were being built, there was a decision made, a small, careful, rather wonderful decision. The first satellite in the series, the NTS-2, the Navigation Technology Satellite 2, launched in 1977, would carry not just a clock tuned to the relativistic offset. It would carry a switch to turn relativity on or off. Not literally turning relativity on or off, of course. The universe is not persuaded by switches. But the clock's frequency synthesizer was built with the ability to be commanded from the ground to either include or exclude the relativistic frequency offset. Mission controllers could, by sending a radio command, choose whether the satellite's clock was broadcasting with the correction applied or without it. And when the satellite reached orbit, that is exactly what they did. They turned the correction on, they watched the clock, they measured its rate against clocks on the ground, and the measured rate change matched the prediction from Einstein's equations. Closely, accurately. The confirmation they had been uncertain about arrived quietly in the telemetry from a satellite in medium Earth orbit in 1977. Carol Alley and Friedwart Winkler were among those involved in that confirmation, working through the measurement and analysis. It was not a press conference moment, it was an engineering result, terse and technical, delivered in data. But what it meant was that the system could be trusted and the correction should be left on. And it has been left on in every GPS satellite, in every navigation constellation, in every receiver you have ever used ever since. We are drifting towards something in this story. The full picture of the engineering, the additional live corrections, the experimental ancestors that built up to this confirmation, and then the wider question of what it means that Einstein is a routine line of code in your pocket. We'll get there, slowly, one piece at a time. But first, I want to let you rest in what we've covered so far. Two effects, not one, not cancelling, two real, separate, physically distinct things, each with its own sign and its own magnitude. Special relativity subtracts 7.2 microseconds per day because the satellite moves fast. General relativity adds 45.9 microseconds per day because the satellite is high. The net is 38, 7 microseconds per day, GPS clocks running fast, the gravitational effect dominant, the drift monotonic and relentless, and amounting to about 11 kilometres of positional error if nothing is done about it. And something is done about it. Something was always going to be done about it. The something in question is a clock set to the wrong frequency on purpose, a passive, mechanical correction derived from equations written by a patent clerk in Bern in 1905 and 1915, waiting patiently to be made right by the universe as the satellite rises. The crossover altitude is 3,200 kilometers. GPS orbits at 2,200. The correction is 10.229999543 megahertz. The first satellite carried a switch, and when they turned it on, the universe agreed with Einstein. That is where we are, and there is more ahead. The additional layer of correction, the experimental ancestors, the global scale of what this all means. But for now, let the numbers settle. Let the image rest. Gravity wins. At GPS altitude, it always wins above 3,200 kilometers, and the clocks above your head are always running a little fast. No rush. We'll carry on in a little while. So, let's carry on. We left off with the number 38 microseconds per day, 38 millionths of a second. And if you haven't fallen asleep yet, and that's perfectly fine if you have, this will still be here in the morning. I want to sit with that number for a moment before we talk about what's done about it, because I think the number deserves a little more time. It deserves to be felt, not just stated. 38 microseconds doesn't sound like much. It really doesn't. If someone told you that your watch was off by 38 millionths of a second, you'd probably shrug. You'd never notice. In the span of a human day, 86,400 seconds of breathing and walking and thinking and sleeping, 38 microseconds is almost nothing. A rounding error. A whisper. But GPS doesn't work in human time. GPS works in the time of light. And light is patient in a very particular way. Light does not forgive small errors. Light moves at 299,792,458 meters per second. That's the number, Sile, precisely that, not an approximation. And if you want to know what 38 microseconds means to a thing moving that fast, you multiply and you get your answer, and the answer is not a whisper. 38 microseconds multiplied by the speed of light gives you roughly 11 kilometers, 11,000 meters. 11 kilometers of accumulated position error growing every single day in the same direction without pause. Your map app would not round that away. Your map app would show you 11 kilometers from where you actually are by the end of the first day, and then 22 kilometers by the end of the second, and 33 by the end of the third. I want you to hold that image for a moment. You open the navigation on your phone. You want to drive to a hospital, or find the nearest petrol station, or meet someone at a train station in an unfamiliar city, and the little blue dot, the one that is supposed to be you, is sitting 11 kilometers away from where you're actually standing. By the time a week has passed, 77 kilometers gone. Not a drift, not a shimmer, a clean, directional, monotonic march away from truth. Monotonic. That word matters. It means the drift doesn't wobble, it doesn't fluctuate and sometimes correct itself. It goes in one direction, always, because the physical cause is always present, always acting and always adding up. The satellite's clock gains time on the ground clock, every second, every orbit, every day, and each gained microsecond is another fraction of a kilometre added to the growing gap between where the system thinks you are and where you actually are. After a fortnight, 2 weeks, you'd be more than 250 kilometres wrong. After a month, somewhere between 300 and 400 kilometres adrift. The phone in your pocket would still be blinking cheerfully, still drawing a blue arrow pointing you confidently down a road, and every instruction it gave you would be useless. This is not a thought experiment, this is arithmetic. Speed of light times 38 millionths of a second equals 11 kilometers per day, compounding.
And here's the thing that I find quietly astonishing about it. The system doesn't drift like this in practice, not because someone is continuously patching it in real time, scrambling to compensate for an emergency. Not because the physicists got lucky, but because the correction was built in, literally built into the clock, before the satellite ever left the ground.
Let me tell you how that works, because it's one of the cleverest pieces of engineering I know of, and the fact that it's been done quietly, without fanfare, for decades, is the kind of thing that should make you feel both humble and amazed at what humans have managed to figure out. Every GPS satellite carries an atomic clock. Actually, it carries several, typically a mix of rubidium frequency standards and cesium frequency standards, because redundancy in space is not optional. These are not the clocks on your kitchen wall. These are devices that measure time by watching atoms oscillate, by counting the natural, unchanging, deeply consistent frequency at which certain atoms vibrate when they're tickled by microwaves or lasers. Cesium-133 atoms, for instance, oscillate at exactly 9,192,631,770 cycles per second. That's not a number engineers chose. That's a number the universe assigned, built into the atom, the same on Earth and on a satellite and on the other side of the galaxy. That's what makes an atomic clock trustworthy. It doesn't drift the way a spring or a quartz crystal drifts. It obeys physics that doesn't change. The GPS system's primary reference frequency is 10.23 megahertz, 10,230,000 cycles per second. This frequency is derived from those atomic oscillations and drives everything. The timing signals, the navigation message, the whole architecture of how the satellites communicate. If the satellite's clock runs at exactly 1023 megahertz in orbit, then every timing signal it broadcasts is, in principle, trustworthy. But we know what happens if it runs at exactly 1023 megahertz in orbit. It gains 38 microseconds per day relative to the ground clocks, which means, from the ground's perspective, the satellite's clock is not ticking at 1023 megahertz. It's ticking slightly faster. It's ticking at a frequency that, multiplied over a day, is 38 microseconds ahead of where it should be. So the engineers did something elegant. They set the satellite's clock to run slightly slow, not in orbit, on the ground before launch. They detuned it. The nominal frequency is 10.23 megahertz. The actual frequency set into the clock's electronics before it goes up is 10 to 2999543 megahertz. Just sit with that number for a second. 10.22999999943 megahertz. There are 9 nines in a row in there, and then a 5 and a 4 and a 3. The difference from the nominal frequency is tiny, 4.465 parts in 10 to the power of 10, less than half a billionth of a percent. And yet that tiny deliberate detuning is what makes the whole system work. On the ground, that clock ticks just slightly too slowly. If you held it in your hand and compared it to a perfect reference, it would lose a fraction of a nanosecond every second. It would seem, to a very precise measurement, to be lagging. But then the satellite rises. It climbs to 20,200 kilometres. It reaches orbital velocity, 3.5 kilometres per second more or less, roughly 14,000 kilometres per hour. Special relativity begins to slow the clock down, as it always does for anything moving. General relativity begins to speed the clock up, as it always does for anything higher in a gravity well. And the net effect, as we've been through together, is that the clock gains 38 microseconds per day. But because the clock was set to run slow by exactly that much, adjusted in advance, in the factory before launch, the gaining and the preset losing cancel each other out. In orbit, running at its slightly detuned frequency, the satellite's clock now ticks at the correct rate for the ground. Not 38 microseconds fast, not 38 microseconds slow, just right. The universe corrects the clock. Or, more precisely, the engineers set the clock knowing the universe would correct it, and the clock obligingly arrives at the right rate once it's where it belongs. It's a bit like setting your watch 5 minutes fast before a long flight, knowing you're heading somewhere with a 5-minute time difference, and arriving to find your watch now shows the right local time. Except instead of 5 minutes, it's 38 millionths of a second per day, and instead of a time zone, it's the curvature of space-time. But the logic is the same. Anticipate the change, build it in. Let physics do the rest. Now, and I want to be honest with you here, because there's a detail that I glossed over a moment ago, and it deserves its own space, this pre-launch correction handles the big, steady, predictable part of the relativistic offset, the average drift. The background hum of time running faster at altitude. But GPS satellites don't orbit in perfect circles. Their orbits are slightly elliptical. And that ellipticity, the slight egg shape of the path, means that during every orbit, a satellite gets a bit closer to Earth and then a bit further away. It gets a bit slower and then a bit faster. And because the relativistic effects depend on both altitude and speed, and both altitude and speed are changing over the course of each orbit, the relativistic offset isn't perfectly constant. It wobbles. It oscillates slightly around the average. Each orbit, the correction needed goes a little above the preset value, then a little below, then back up, cycling around as the satellite traces its ellipse. This oscillating wobble, the technical name for it is the eccentricity correction, can amount to up to about 45 nanoseconds above or below the expected value, depending on the specific orbit's shape. 45 nanoseconds might sound small, but remember, 1 nanosecond of timing error equals 30 centimetres of position error. 45 nanoseconds is about 13.5 meters of error, swinging back and forth over every single orbit, which takes roughly 12 hours. That's not nothing. That's the difference between knowing your car is in the right lane and not knowing. So the pre-launch frequency offset handles the steady background. And then your receiver, the chip inside your phone, the little sliver of silicon doing its math while you tap your destination into the map, computes the eccentricity correction itself in real time for each satellite it's listening to. There is an actual equation for this. It's written into the official GPS interface control document, the public engineering specification called IS-GPS 200, the document that defines how the system works and how receivers must behave. And in that document, nestled among pages of orbital parameters and signal formats, is a relativistic correction term. It reads roughly as negative 2 times the square root of the product of the gravitational parameter and the orbital semi-major axis times the orbital eccentricity times the sign of the eccentric anomaly, all divided by the square of the speed of light. If that string of symbols makes you drowsy, that's perfectly all right. The point is simply this: it's there, it's written down in a government document, published, available to anyone who wants to read it. Relativity is not a secret ingredient that some physicist whispers to the engineers over the phone. It's a line of math in the public spec. It's policy, and the receiver in your pocket implements that equation. Every few seconds, when it's pulling timing signals from the constellation above, it applies that correction to each satellite's clock reading. It's doing Einstein's geometry live in your hand as you try to figure out which coffee shop is closest. But there's still one more correction in the stack, and this one is a bit different. It comes not from the satellite's speed or altitude, but from the Earth's rotation. Think about the geometry for a moment. A GPS satellite is broadcasting a signal from 20,000 kilometers up. That signal travels at the speed of light. But even at the speed of light, it takes time to reach you, about 0.07 seconds, 68 milliseconds or so. And during those 68 milliseconds, the Earth has not been sitting still. It's been rotating. You've been rotating with it. The ground beneath you has moved. A small amount, but not nothing. A few centimetres at typical latitudes, sometimes more. So by the time the signal arrives and your receiver tries to calculate its position, the coordinate frame has shifted slightly underneath everything. The satellite was at position A when it broadcast. You were at position B when you received it. But the Earth has rotated, so A and B are in slightly different reference frames than the math assumes. This effect is called the Sagnac effect, after the French physicist Georges Sagnac, who described the principle in 1913. When you're working in a rotating reference frame, which the Earth absolutely is, and you send light or radio waves across that rotating frame, there's a geometric mismatch between the traveling signal and the rotating coordinate system. For GPS, depending on the geometry, the angle between satellite and receiver, the latitude, the length of the signal path, the Sagnac correction can range from tens of nanoseconds to a couple of hundred nanoseconds. Again, nanoseconds to hundreds of nanoseconds, 30 centimetres to perhaps 60 metres of position error lurking in the geometry of Earth's rotation. And again, the receiver computes this, quietly, continuously, every time it calculates a position. When you look at what your phone is actually doing when you open a map, then, and I find this genuinely wonderful to contemplate, even half asleep, it's not just finding a signal and reading off your position. It's correcting for the bending of time by gravity. It's correcting for the slowing of time by speed. It's correcting for the oscillation of those effects as the satellite traces its ellipse, and it's correcting for the rotation of the planet you're standing on. All of this all at once in a chip the size of your thumbnail in a fraction of a second, so that the little blue dot lands in roughly the right place. The whole correction stack, pre-launch frequency offset plus eccentricity correction plus Sagnac correction, is what stands between your phone knowing where you are and your phone being worse than useless. And for a while, in the early days of the GPS program, not everyone was convinced all of this was necessary, not the general relativity part, especially. This is where the story gets interesting, and I want to tell it to you gently because it's a story about scientific caution, about not wanting to believe something until you've seen it with your own instruments. And that caution, in retrospect, is rather beautiful. By the mid-1970s, the GPS system was being designed and built in earnest. The theoretical case for the relativistic correction was solid. The mathematics had been checked, the effects had been calculated, the 38 microseconds per day was not a guess. But there's a difference between a calculation and a measurement, and some of the engineers and scientists involved in the program were not prepared to bet the navigation accuracy of a global system on a relativistic correction that had never been directly verified at GPS altitude in a GPS-like clock in orbit. The concern was reasonable. The relativistic effects that had been measured to that point, and we'll talk more about those measurements in a while, had mostly been done in different regimes, different altitudes, different velocities, different instruments. Extrapolating those measurements to exactly the GPS case required a chain of theoretical steps, and some people wanted to close that chain experimentally before committing to it in the design. So they did something rather remarkable. When the Navigation Technology Satellite 2, NTS-2, was launched in 1977, the engineers included a switch, not a metaphorical switch, an actual, commandable, physical switch built into the frequency synthesizer of the satellite's cesium clock. A switch that, when in one position, included the relativistic frequency offset, the pre-tuning down to 10 to 19.9543 MHz, and when in the other position removed it, letting the clock run at the nominal 1023 MHz with no relativistic pre-correction. The idea was this: put the satellite in orbit, turn the switch one way and measure what happens, turn it the other way and measure what happens, compare the results to what Einstein predicts, and let the universe tell you whether the correction was needed. The physicists involved in analyzing those results included Carol Alley from the University of Maryland, who had spent years working on precision timing and relativistic effects in clocks, and Friedwert Winkler, whose work on clock comparisons had helped lay the groundwork for this kind of measurement. And when the data came back from NTS-2, it was clear. With the switch in the uncorrected position, the clock running at 1023 MHz, the satellite's clock drifted ahead, exactly as Einstein predicted. Exactly the roughly 38 microseconds per day accumulated from the two effects working in opposite directions and failing to cancel at GPS altitude. And when the correction was switched on, the pre-offset engaged the clock running at 10.229 9543 MHz. The drift went away. The clock stayed in step with the ground, orbit after orbit, day after day. The universe agreed with Einstein, in orbit, with a real clock, on a real satellite, measured by real instruments. The switch was the experiment, and the result of the experiment was the same as the result Einstein's mathematics predicted 50-some years earlier from a patent office in Bern. From that point on, the correction wasn't optional. It wasn't a philosophical debate. It was data. And every GPS satellite launched after NTS-2 has included the pre-tuned frequency as a matter of standard engineering practice, because the alternative, not correcting, was demonstrated in orbit to produce exactly the error budget that the theory predicted. There's something I find deeply satisfying about this. The engineers who included the switch weren't being obstinate. They weren't being anti-Einstein. They were being scientists. They wanted a measurement, and they got one, and the measurement was unambiguous. That's how this is supposed to work. You build the switch, you turn it on, the universe speaks, you listen, and then you never have to wonder again. Now, I want to stay with the receiver for another moment because I think there's something here that doesn't get talked about enough. We've established that the satellite's clock is pre-corrected at launch, tuned to run slow on the ground so that it runs right in orbit. But that only handles the average steady component of the relativistic offset. The eccentricity correction and the Sanak correction, those happen on the ground, in your receiver, in real time, which means your phone is doing relativity. Every time your navigation app is open, the chip inside your phone is receiving signals from several satellites simultaneously, typically 4 or more, because you need at least 4 to get a 3-dimensional position fix. And for each one, it's computing a small relativistic correction based on where that satellite is in its orbit at this particular moment. Not a single pre-computed number, a different calculation per satellite, per position in its orbit, every few seconds. The eccentricity correction depends on the satellite's orbital eccentricity, how elliptical its path is, and on the satellite's current position in that ellipse, which is described by a quantity called the eccentric anomaly. These values are broadcast by the satellite itself as part of its navigation message, the stream of data embedded in the signal, and your receiver reads them and plugs them into the formula. The formula involves the square root of quantities derived from Newton's gravitational parameter and the orbital geometry divided by the square of the speed of light. Your phone computes this in the background without being asked, while you're deciding whether to turn left or right. And the Sagnac correction depends on the geometry of that particular satellite's position relative to your particular location on the rotating Earth at this particular moment. Different satellite, different angle, different correction, different location, different correction. So even that one isn't a single fixed number. It's a calculation your receiver makes fresh each time for each bird in the sky above you. Collectively, the relativistic corrections your receiver applies can amount to something in the range of tens to hundreds of nanoseconds per satellite per measurement. And since each nanosecond is about 30 centimetres of position error, and since the receiver is pulling measurements from 4 or more satellites simultaneously and triangulating between them, trilateration, strictly speaking, not triangulation, but the word is close enough for a sleepy night, those corrections matter. Remove them, and the accuracy of your position, fix, degrades, keep them, and the little blue dot stays honest. The GPS receiver in your phone contains in its firmware, the software baked into the chip itself at the factory, a relativistic correction algorithm. There is no user-friendly version of this. It doesn't appear in any menu. There's no setting you can toggle that says enable Einstein. It just runs. It has always run. It will run every time your phone looks at the sky and asks where it is. Physics isn't a feature, it's the flaw. And I want to sit with that for a moment because I think it's one of those facts that sounds simple and then gets slowly more astonishing the longer you think about it. We live in a world where the most mundane act of everyday navigation, finding a restaurant, following a delivery, making sure the ride arrives at the right corner, depends continuously and silently on the two most exotic theories of physics produced in the 20th century. Special relativity, which says that moving clocks tick slow, derived from Einstein's 1905 paper. General relativity, which says that high clocks tick fast, derived from his 1915 paper, both running simultaneously, both corrected for, both leaving a measurable physical trace tens of thousands of kilometers overhead and in the silicon of a chip the size of a fingernail. That's not folklore. That's not a metaphor. That's the engineering record. And if you're the kind of person who has perhaps encountered the phrase, Einstein's theories have never been tested in everyday life, then GPS is your answer. GPS is the test. Running right now, 6 billion phones consulting it. Every measurement of position that comes back correct is a verification, one more data point in the largest confirmation of general relativity in human history. Which brings us, naturally, gently, the way a good night's conversation drifts from one warm room to the next, to the question of how we knew any of this before the first satellite ever flew. How did the GPS engineers know the correction to use? Where did the confidence to build NTS-2 with a switch, rather than simply assuming the theory was wrong and not bothering, come from? It came from a chain of experiments, each one building on the last, each one tightening the chain of evidence until the theory was not a guess, but a fact. Let me tell you about those experiments. We'll take them in order, slowly, because they each have their own character, their own ingenuity, and together they tell the story of how physicists learned to take relativity seriously, not as an abstraction, but as something you could measure with instruments you had built with your hands. The first of the three I want to tell you about is the one that comes earliest, and in some ways the one I find most striking, because of what it used to make its measurement. This was the Pound-Rebka experiment carried out in 1959 at Harvard University. The physicists involved were Robert Pound and his graduate student Glenn Rebka, and what they were measuring was gravitational redshift, the phenomenon whereby light climbing out of a gravitational field loses energy, its frequency dropping, its color shifting toward the red end of the spectrum, precisely because it's climbing against gravity. The general relativistic prediction is that a photon of light emitted from a lower gravitational potential, deeper in a gravity well, closer to a massive object, will arrive at a higher potential having lost a small amount of energy. It will be slightly redshifted, and equivalently a clock ticking at a lower gravitational potential will appear to run slow when compared to a clock ticking at a higher potential. These are two ways of saying the same thing. Time runs slower where gravity is stronger. Einstein's theory predicted this, but the effect at Earth's surface over any reasonable laboratory distance is extraordinarily small. Pound and Rebka wanted to measure it over a height difference of just 22.5 meters, the height of a tower in the Jefferson Physical Laboratory at Harvard. 22.5 meters, a building, not 20,000 kilometers, not even a kilometer. 22.5 meters, the frequency shift over that height is roughly 2.5 parts in 10 to the power of 15. That's 2.5 parts in a quadrillion. 1 part in 400 trillion. This is a number so small that for most of human history it was simply inaccessible. No instrument sensitive enough existed. What changed in 1958 was the discovery of the Mersbauer effect, a phenomenon in nuclear physics where certain atomic nuclei, when embedded in a crystal lattice, can absorb and emit gamma rays at extremely precise, narrow frequencies without the usual blurring caused by the thermal motion of free atoms. Rudolf Mersbauer had discovered it, and it would earn him a Nobel Prize in 1961. And what it gave Pound and Rebka was a kind of gamma-ray tuning fork, a way to emit and then detect gamma rays at frequencies precise enough to see the gravitational shift over 22 meters. They sent gamma rays down the tower, up the tower. They measured the tiny shift in frequency as the photons climbed and descended against Earth's gravity, and the result, to roughly 10% accuracy initially and later improved to about 1%, matched Einstein's prediction. 22.5 meters. A building. Light climbing a flight of stairs and measurably aging differently from light descending it. The Pound-Rebka experiment was, in 1959, the first precise laboratory confirmation of gravitational time dilation. It showed that the effect Einstein had predicted wasn't just a property of exotic astronomical objects, black holes and neutron stars and collapsing supernovae, but was present, real, and measurable in a university physics building in Cambridge, Massachusetts, over the height of a modest tower. And it laid the experimental groundwork for everything that came after, including GPS. The second experiment happened in 1971, and it had a different character entirely. This one didn't use a tower or a laboratory, it used commercial airliners. The physicists were Joseph Haufel, a physicist from Washington University in St. Louis, and Richard Keating, a time scientist at the U.S. Naval Observatory. Their idea was straightforward in principle and enormously fiddly in practice. They would take portable cesium atomic clocks, the best available, onto commercial flights around the world, eastward on one trip, westward on another, and then they'd compare those clocks when they came home to reference clocks that had stayed behind at the Naval Observatory in Washington. The prediction involved both relativistic effects. The flying clocks would be at higher altitude than the ground clocks, so gravitational time dilation would make them tick faster. But the flying clocks would also be moving faster than the ground clocks, so velocity time dilation from special relativity would make them tick slower. And because the Earth is rotating, eastward flights add the plane's speed to the Earth's rotation speed, making the clocks move faster overall, while westward flights subtract, making them move slower overall. So the two trips would produce different results, and the theory made specific, quantitative predictions for both. In October 1971, Haufel and Keating did it. They bought seats on commercial flights, apparently rather uncomfortable ones, surrounded by curious fellow passengers, and with cesium clocks stacked in the seats beside them. and flew around the world eastward and then westward. The flights took several days each. The clocks ticked away, recording time as best they could at 35,000 feet. When the clocks came home and were compared to the Naval Observatory referenced, the results were striking. The eastward clocks had lost time. They ran slow compared to the ground, as the combined speed effect slightly dominated. The westward clocks had gained time. They ran fast compared to the ground, as the altitude effect dominated over the reduced speed. Both results matched the predictions of special and general relativity within the experimental uncertainties. It wasn't perfect. The experimental uncertainties were substantial. The clocks of 1971 were good, but not as precise as what came later, and the timing of the flights introduced its own complications. But the pattern was there, unmistakably. Both effects, opposite signs for the two directions. Quantitative predictions from theory met by quantitative results from experiment. Haffler and Keating published their results in Science magazine in 1972, and what the experiment demonstrated for the first time with macroscopic, portable, real-world clocks you could carry aboard an aeroplane, not just mount in a laboratory tower, was that relativistic time differences accumulated over a journey. The clocks went out, they came back, and they disagreed with the ones that had stayed home, by exactly the amounts that Einstein said they would. This was a direct, conceptual predecessor to what GPS would need, not gamma rays in a tower, not hypothetical atomic oscillations, real atomic clocks carried through real motion at real altitude, time that diverged and could be measured. The third experiment, Gravity Probe A, came in 1976, and it pushed to much higher altitude, directly into territory more comparable to the GPS regime. The device was a hydrogen maser, a type of atomic clock that uses the natural oscillation frequency of hydrogen atoms, which vibrate at about 1.4 gigahertz. Hydrogen masers are among the most stable clocks ever built for short to medium timescales, and in 1976 a specially built one was prepared for spaceflight. The experiment was simple in principle. Launch the hydrogen maser on a rocket to an altitude of about 10,000 kilometers, compare its frequency to an identical reference maser on the ground during the 2-hour flight, and measure the gravitational redshift. The rocket was a scout rocket, uncrewed, and the flight was a short ballistic arc up and back down over the course of roughly 2 hours. The altitude reached, around 10,000 kilometers, was roughly halfway to GPS orbit. At that altitude, the gravitational effect on the clock was significant and measurable, and the prediction from general relativity was specific. The flying maser should tick faster than the ground maser by a precisely calculable amount, depending on the altitude profile of the flight. The result confirmed the gravitational redshift, the gravitational time dilation, to about 70 parts per million. 70 parts per million means the measurement agreed with Einstein's prediction to about 0.007%. That was, at the time, the most precise direct confirmation of gravitational time dilation in the regime closest to GPS operation. Pound and Rebka at 22.5 meters, Haffler and Keating on an aeroplane, Gravity Probe A at 10,000 kilometers, each experiment climbing higher, measuring the effect more precisely, in conditions closer to the GPS environment. By the time the GPS program needed to make its engineering decisions, by the time the designers of NTS-2 were deciding whether to include a switch or just build the correction in, the experimental chain was solid. The effect was real. The magnitude was predictable. The only remaining question was whether it would appear exactly as expected in a GPS-type clock at GPS altitude. And then NTS-2 launched, and the switch was flipped. And it did. The chain was closed. Theory to experiment, experiment to engineering, engineering to the firmware in your phone. I find that chain beautiful, in the way that slow, careful things often are. Nothing about it was rushed. The physicists at Harvard in 1959 were not thinking about satellite navigation, GPS didn't exist yet, and the space age had only just begun. Hafele and Keating were not building GPS technology, they were checking whether you could detect relativistic time differences with clocks you could carry. Gravity Probe A was a fundamental physics experiment, not an engineering test, and yet each piece was waiting, patient and precise, to become necessary. By the time it was necessary, by the time the GPS program needed to know whether to correct for Einstein or not, the answer was already there. In 3 different experiments, at 3 different scales, using 3 different methods, all converging on the same number, the same ratio, the same effect. Time runs faster when you're higher up. The higher you are, the more it runs fast. At GPS altitude, it runs fast enough that, uncorrected, you'd be 11 kilometers wrong by nightfall. And so the clock is set to 10^9999543 megahertz. And the switch on NTS2 was the proof. And the receiver in your pocket does the live math, and the blue dot stays where it should be. We've covered a lot of ground tonight, quietly, slowly, one thing at a time, and there's still more to come. The full scale of what GPS means as a confirmation of Einstein, the global family of navigation systems that all do the same corrections, and the question of what all of this says about the universe we live in. But let that rest for now, just ahead of us, waiting gently in the next part of the night. Because here, at this point in the story, something has shifted. We started with the number, 38 microseconds, 1 day of drift, 11 kilometers of error, and we followed it back through the engineering to the physics, and through the physics to the experiments, and through the experiments to the moment someone built a switch and let the universe answer for itself. And the universe answered. That's worth holding for a while if you're still with me, wherever you are. In your bed, on your sofa, in whatever corner of the world is quiet around you right now, the universe answered. In orbit, with a cesium clock, measured by instruments that humans built with knowledge that Einstein published from a patent office in 1905 and 1915, before aeroplanes crossed oceans regularly, before the idea of a satellite was science fiction rather than science. And the answer matched the equations. It always does, and that, perhaps, is where we should linger for a moment before moving forward. Because what we've been circling around, what the number 38 microseconds and the switch on NTS2 and the pre-tuned clock all point back toward, is a much older story. A story that began not with satellites or software or the device in your pocket, but with a staircase, with a tower, with 2 physicists at Harvard University in 1959 who decided to ask whether time itself could be measured running at different speeds across a distance you could walk in 10 seconds. Their names were Robert Pound and Glenn Rebka, and what they did was both beautifully simple and astonishing. The Jefferson Physical Laboratory at Harvard had a tower, modest as towers go, rising about 22.5 meters from its basement to its roof. 22.5 meters, you could climb it in under a minute. You've stood in buildings taller than it without noticing, and Pound and Rebka placed a source of gamma rays at the bottom of that tower and a detector at the top, and they asked a question that Einstein's general relativity had already answered on paper, but that nobody had yet confirmed in a laboratory with this kind of precision. The question was, does gravity change the frequency of light? And here's what that means in plain terms. Imagine you're standing at the bottom of the tower with a bell, and you ring it once every second, and someone at the top counts the rings. Einstein's prediction, the gravitational redshift, says that from the perspective of the person at the top, your bell is ringing ever so slightly slower. Not because you're ringing it differently, but because time at the bottom of the tower, deeper in the gravitational field, runs ever so slightly slower than time at the top. A gamma ray is, in a sense, an extraordinarily fast bell. It has a frequency. It oscillates at a specific rate. And if it's emitted at the bottom of the tower and detected at the top, the detector should see it oscillating at a very slightly lower frequency than it was emitted. The gravity well has stretched it, ever so slightly, as it climbed. The problem is that ever so slightly really means it. The fractional frequency shift over 22.5 meters is roughly 2.5 parts in 1,000 trillion. That is a number so vanishingly small that measuring it in 1959 should not, by any ordinary measure, have been possible. But Pound and Rebka had something that made it possible. They used the Mössbauer effect, a technique discovered just a year or two earlier by Rudolf Mössbauer that allows atomic nuclei in a crystal lattice to emit and absorb gamma rays with extraordinary sharpness, making them exquisitely sensitive detectors of tiny frequency shifts. They moved the source at a controlled velocity, using the Doppler effect to precisely tune the emitted frequency, and looked for the resonance, the exact speed at which the Doppler shift exactly compensated for the gravitational shift. And they found it. The measured shift matched Einstein's prediction to within about 10%. Later, more refined versions of the same experiment brought that agreement down to about 1%. It was the first direct, precise laboratory confirmation that gravity does something to time, not to clocks built by humans, not to mechanical things that wear out or drift, to the fabric of time itself as expressed in the frequency of light. 22.5 meters, a tower you could climb in under a minute, and time was measurably different at the top and the bottom. This is the experiment that sits at the root of everything the GPS satellites do. The Pound-Rebka experiment is, in a sense, the proof of concept for the whole correction stack. It confirmed that Einstein's gravitational time dilation is not a mathematical curiosity, but a physical reality that shows up at ordinary scales, with ordinary distances, using instruments built by human hand. But Pound and Rebka could only measure the effect across a fixed tower in a controlled lab. The next question was whether it survived motion. Whether you could carry a clock on a journey and bring it back and see the same effect in the accumulated time difference. That question fell to two physicists named Joseph Haffel and Richard Keating. It was 1971. Haffel and Keating did something almost comically straightforward for an experiment testing the fundamental nature of time. They bought seats on commercial aircraft, regular passenger flights, and they brought cesium atomic clocks with them. Accurate, portable, real atomic clocks tucked into passenger seats, crossing the world at ordinary aircraft altitudes and speeds, eastward and then westward, while a reference clock sat quietly back at the United States Naval Observatory in Washington. When they returned and compared the clocks, the traveling ones had drifted, slightly, measurably. Both special and general relativistic effects showed up in the numbers. The clocks that had flown eastward, moving fastest relative to the ground because they were flying in the same direction the Earth rotates, came back running a little slower from the velocity effect, slightly counteracted by the altitude effect. The westward clocks showed a different combination. Both matched the predictions from Einstein's equations within the margins of experimental error. Time had passed differently for the clocks on the planes. Not by much, by a few hundred nanoseconds, a few hundred billionths of a second. You would not have noticed it. You could not have felt it. But it was there, and it was measured, and it matched. What Haffel and Keating demonstrated was that relativistic time effects are transportable. They come with the clock. They accumulate on the journey. They don't require a laboratory tower or a controlled gamma-ray source. They emerge from the physics of motion and gravity wherever you go, whether you're a physicist or a passenger on a Thursday afternoon flight from New York to London. And the significance for GPS was this. If relativistic effects accumulate on a plane at ordinary altitude and ordinary speed, they certainly accumulate on a satellite at 20,200 kilometers and 14,000 kilometers per hour. The Hafele-Keating experiment established that you cannot simply dismiss this as a lab artifact. It goes with you. Still, the GPS system was still some years away, and what the engineers and scientists needed was a confirmation specifically in the regime that mattered for space-based navigation. Higher altitude where the gravitational effect dominates. That confirmation came in 1976 in an experiment called Gravity Probe A hydrogen maser, a kind of atomic clock that uses the quantum transitions of hydrogen atoms, was launched on a Scout rocket to an altitude of approximately 10,000 kilometers. Not into orbit, it went up and came back down on a suborbital trajectory, a flight lasting only about 2 hours, but those 2 hours were enough. As the maser climbed higher in the gravitational field, its clock rate changed in exactly the way Einstein predicted. The comparison between the signal from the maser in flight and a reference maser on the ground confirmed the gravitational time dilation to an accuracy of about 70 parts per million. 70 parts per million. That's a precision of roughly 0.07%. It was, at the time, the most precise test of the gravitational redshift in the relevant altitude regime. And what it said, unambiguously, was this. At altitudes comparable to satellite navigation orbits, gravity does to clocks exactly what Einstein's equations predict it does, at the exact magnitude the equations specify. Gravity Probe A was in many ways the final proof of concept before GPS began operating. It confirmed that the engineering correction wasn't a theoretical nicety or a safety margin. It was a precise, real, measurable effect that would show up in the data if you didn't account for it, and would ruin your navigation system if you ignored it. So by the time the first fully operational GPS satellites were going up, the experimental lineage was already there. Pound and Rebka had confirmed gravitational redshift in a tower. Hafele and Keating had shown relativistic clock differences accumulate in real transport. Gravity Probe A had confirmed the gravitational effect at the relevant altitude with the relevant precision. The physics was not in dispute. The question was only whether the engineering implementation could match it. And the switch on NTS-2 launched in 1977 answered that. Which brings us to what GPS is in the long view. GPS is often described as a navigation system, and it is. But describing it only that way is a little like describing a symphony as a collection of vibrations, technically accurate, missing what matters. What GPS actually is, or looked at from a certain angle, is the largest, most continuously run verification of general relativity in the history of physics. Not a laboratory experiment, not a single rocket flight, not a pair of physicists on a Thursday afternoon flight with borrowed atomic clocks. A permanently operational planetary system with 24 or more satellites, monitored continuously, with the relativistic correction running every second of every day, confirmed billions of times over by the simple fact that the navigation works. Every time you open a map app and the blue dot appears where you actually are, not in the wrong town, not 11 kilometers off, but here, where you're standing, you are confirming Einstein. Not in any dramatic, ceremonial sense. Just quietly, routinely, billions of times a day. The relativistic correction is running and the blue dot is right, and that's the confirmation. This is something worth sitting with for a moment. Before GPS, general relativity was confirmed by a handful of observations and experiments, beautiful ones, precise ones, but each requiring careful setup and deliberate measurement. Mercury's orbit precesses at the rate Einstein's equations predict. Light bends around the Sun, as Arthur Eddington's 1919 eclipse observations showed. Gamma rays shift their frequency, climbing a 22.5-meter tower. Clocks on aircraft come back slightly out of sync. A hydrogen maser on a suborbital rocket shows the right clock rate at altitude. All of these are real confirmations. All of them matter. but they are, in a sense, measurements you go out to make at specific times and places for the specific purpose of testing the theory. GPS is different. GPS doesn't test general relativity. GPS uses general relativity. Every nanosecond, every satellite, every receiver, every map app. The confirmation isn't something a physicist has to go set up. It's something that's been continuously happening at the scale of planetary infrastructure since the first operational satellites went up in the late 1970s and early 1980s. Every time the system works, it's another data point, and the system works billions of times a day. If general relativity were even slightly wrong, if the gravitational time dilation were a little smaller or larger than Einstein's equations predict, the correction baked into those clocks at 10 to 299.99543 megahertz would be the wrong correction, and the drift would be the wrong amount, and the blue dot would wander, and people would notice, because people notice when their map app puts them on the wrong street. The fact that it doesn't wander is the experiment, running constantly, on a global scale for decades. And the correction isn't just used by GPS. Every satellite navigation system in the world applies the same physics, because the same physics governs every satellite in the same regime. Russia's GLONASS constellation, their equivalent of GPS, which has been running since the Soviet era and continues today, applies relativistic corrections to its satellite clocks. The orbits are slightly different in inclination and altitude compared to GPS, but the fundamental physics is the same, and the corrections are calculated accordingly. Europe's Galileo system, operated by the European Space Agency and the European Union, does the same. The Galileo satellites orbit at a slightly higher altitude than GPS, about 23,022 kilometres, which means the gravitational time dilation is even larger at Galileo's altitude and the correction is even more significant. The engineers calculated it, designed for it, and built it in using the same Einstein equations. China's Beidou navigation satellite system, which has grown into a global constellation over the past 2 decades, does exactly the same thing. Relativistic clock corrections, both effects, the full treatment. Every country, every consortium, every navigation satellite system. The physics doesn't care about national borders or engineering philosophies or political arrangements. Gravity is gravity. Velocity is velocity. Einstein's equations describe both, and everyone who wants to build a satellite navigation system that works has to do the same calculation and apply the same correction. This is, when you think about it, a remarkable kind of universality. The equations written down by one person in the early 20th century, a person who often doubted whether his more exotic conclusions would ever be practically relevant, are now not the intellectual property of any one country or institution. They're just part of the engineering standard. They're written into the IS-GPS 200, the interface control document that specifies exactly how the GPS system works, including the exact form of the eccentricity correction term that receivers compute. They're in the equivalent documents for GLONASS, Galileo, and Beidou. They're in the firmware of the chip in your phone. They're running right now in orbit, above your head, above everyone's head, in satellites carrying flags from 4 different political entities, all of which agree because they have to, because the universe insists on the same fundamental correction. Einstein as a universal engineering standard, that's what we've arrived at. Now, the system itself, the engineering architecture around all of this physics, has a quiet elegance worth understanding, even at sleep pace, even in the few minutes before you drift. There are at least 24 GPS satellites operational at any given time, usually more. As of recent years, the constellation typically runs with 31 or more satellites active, which gives more coverage and better geometry at any location on Earth. They fly in 6 orbital planes, arranged around the Earth like the seams on a loosely woven ball, tilted at about 55 degrees to the equator. Each satellite completes one orbit in approximately 11 hours and 58 minutes, very close to exactly half of one sidereal day, which means that each day the geometry of the constellation repeats almost exactly, which simplifies the planning and prediction of coverage. These satellites are not autonomous. They don't just float up there and figure things out on their own. They're managed continuously from the ground. The heart of that management is the Master Control Station at Schriever Space Force Base in Colorado, a facility that monitors all the satellites in the constellation, tracks their clocks and orbits, computes any residual errors, and periodically uploads corrections. The satellites have their own high-precision atomic clocks, yes, both rubidium and cesium standards. But even the best atomic clock drifts slightly over time, and even the best pre-launch frequency offset needs occasional adjustment as the hardware ages. So the ground station watches and it corrects, and the system stays calibrated. There's also a timekeeping subtlety that's easy to miss in the bigger story. GPS runs on its own timescale called GPS time. GPS time started at midnight between January 5th and January 6th, 1980. And unlike the timescales you see on your phone's clock, GPS time does not include leap seconds. Coordinated Universal Time, UTC, the standard timescale that the world uses, occasionally adds leap seconds to stay in sync with the Earth's rotation, which is slightly irregular. GPS time doesn't do that. It keeps running second after second without those adjustments. This means GPS time and UTC have diverged. As of recent years, GPS time is 18 seconds ahead of UTC. Your phone automatically handles this conversion. It knows the offset and adjusts. But the point is that even the definition of what a second means and how many of them have passed since a reference point is something the system has to carefully manage. Timekeeping at this level of precision has layers within layers, and over all of it, the atomic clocks, the orbital planes, the ground station, the leap second handling, the pre-launch frequency offset, the receiver side eccentricity corrections, over all of it, quietly and continuously runs the relativistic correction. 38 microseconds per day, 45 microseconds up, 7 microseconds back, net 38, always. Without rest, in every satellite, for every user, everywhere. Your phone receives signals from at least 4 of these satellites simultaneously when you open a map. Each signal carries a timestamp from that satellite's atomic clock, a clock that is running at the right rate because its frequency was tuned before launch to account for Einstein, and because your phone is doing its own live correction for the orbital eccentricity and the Sanak effect from Earth's rotation. Your phone compares those timestamps, works out how long each signal took to travel from each satellite to your receiver, multiplying by the speed of light to convert time to distance, and solves a set of equations to determine where in three-dimensional space you must be for all those distances to be consistent. That point in space is where you are. And then the little blue dot appears on your screen, sitting exactly where your bed is, or your sofa, or your kitchen table, calm, certain, unremarkable, all of that happening in the time it takes you to blink. Now, I want to take a moment to say something about Einstein. Albert Einstein published Special Relativity in 1905. He was working at the patent office in Bern, Switzerland. He published General Relativity, the gravitational piece, the part that explains why clocks run at different rates at different heights. In 1915, he was 36 years old. And throughout his life, Einstein was often uncertain, and sometimes openly doubtful, about whether his more exotic conclusions would ever mean anything in the practical world. The effects of general relativity, he knew, were tiny at the scales humans normally inhabited. A few parts per billion here, a few nanoseconds there. In the world of 1905 or 1915, there was no instrument sensitive enough to care about a nanosecond. There was no application that required it. The effects were real. Einstein believed they were real, but he also believed they were far beyond the reach of any ordinary engineering. The universe was stranger than Newton had known, but the strangeness lived in the very large. The bending of light around stars, the orbit of Mercury, or in the very small and the very fast, in regimes of physics that seemed safely remote from anything as mundane as getting from one place to another. He could not have imagined GPS, not the satellites. The idea of artificial satellites was barely beginning to take shape in the last years of Einstein's life, and he died in 1955 before Sputnik. Not the atomic clocks. The first practical cesium atomic clock came online in 1955, the year he died. Certainly not the idea that his equations would be encoded into a chip inside a device that billions of people carry in their pockets and consult without thinking about it. When Einstein wrote down the equations that describe how gravity curves space-time and how that curvature changes the rate of time, he was trying to understand the universe, not to navigate it, not to build things, to understand. And the understanding he reached was so deep, so precise, so completely correct in its description of how reality actually behaves, that it outlasted every practical context he could have conceived of and became essential infrastructure in a technological world he never lived to see. He is now a routine line of code. That is remarkable. Sit with it for a moment. Not a monument, not a name on a school, not a face on a stamp, though he has those things too. He is, most concretely and continuously, a correction factor, running in every satellite navigation system on Earth, 24 hours a day, 7 days a week, consulted by roughly 6 billion phones, by aircraft navigation systems, by the precision timing networks that synchronize financial transactions, by the infrastructure that keeps power grids stable across continents. Einstein encoded, Einstein operational, Einstein unremarkable, in the best possible sense of that word, so thoroughly confirmed and so completely integrated into the world's working that nobody who opens a map app thinks about it at all. That's what being right looks like at sufficient scale and sufficient time. And here is the thing I want you to carry with you as you drift towards sleep, wherever you are, in whatever corner of the world has gone quiet around you. All of this, the satellites, the atomic clocks, the relativistic corrections, the blue dot on your screen, all of it is ultimately a story about time. Not about technology, not about engineering, about time. About the fact that time is not what it looks like from the inside. From the inside, time feels like a fixed, steady river moving at the same rate for everyone, everywhere. It feels as though the second you're living in right now is identical to the second your friend is living in across the world, identical to the second passing on a satellite 20,000 kilometres above you. It feels that way because we are all, by and large, moving at similar speeds and living at similar altitudes on the surface of the same planet, and the differences are too small for any human sense to detect. But they are there, even at the scale of your own body. We talked about it near the start of our night together, and I want to bring it back now because it means something different at the end of the story than it did at the beginning. In 2010, at the National Institute of Standards and Technology, NIST, in the United States, a team of physicists named Cho, Hume, Rosenband, and Wineland built 2 aluminum-ion optical clocks of extraordinary precision, and they measured the difference in the rate of time across a height difference of 33 centimetres. 33 centimetres, about the length of a standard ruler, about the difference in height between a low pillow and a tall one, about the distance from your shoulder to your elbow, and time was measurably different at the top and the bottom. The higher clock ran faster, by a tiny, nearly unimaginable amount, about 1 part in 10 to the power of 16 per metre of height. Over a human lifetime, the accumulated difference between your head and your feet is tens of billionths of a second, You will never notice it, you could never feel it, but it's there and it's real and it's been measured. Your head is aging very slightly faster than your feet, not because of anything unusual about your head or your feet, but because your head sits slightly higher in Earth's gravitational field, and general relativity says that clocks higher in a gravitational field run faster. The same physics that makes the GPS satellite clocks run fast, the same physics that Pound and Rebka measured in a tower, the same physics that Hafelet and Keating carried around the world on aircraft, the same physics that Einstein published in 1915, the same physics that is running right now in orbit above you, baked into the frequency of an atomic clock tuned to 10.229999543 megahertz. It's not out there somewhere in satellites and laboratories and theoretical physics. It's in here. In you, in your body, right now, as you lie still and let the night settle around you. Your head and your feet are living in slightly different versions of time, and somehow that is not frightening, or it doesn't have to be. It's strange, yes, profoundly, wonderfully strange, but there's something quietly comforting about it too. It means the universe is richer than it looks, more layered, more intricate, more surprising than the flat, uniform mechanical picture that common sense would paint. Time isn't a rigid rail that everything moves along at the same speed. It bends, it stretches, it runs a little faster in the quiet attic than in the basement. It runs faster at your temple than at your toes, and that strangeness, that impossible, verified, physically real strangeness is not something you have to go to a physics laboratory to find. It's not something that requires a telescope or a particle accelerator or a suborbital rocket. It's there in the 33 centimetres between your hair and your pillow. It's there in the signal your phone receives from a satellite that was built with Einstein's equations encoded into the frequency of its clock. It's there in the blue dot on the map that knows where you are because it knows what time it is, precisely, to better than a nanosecond. It's all around you, and you've been relying on it every time you open a map without ever needing to know it was there. I think about that sometimes. The way we move through a world that is built on top of extraordinary things, and how rarely we slow down enough to see what's underneath. The bridge that holds your weight when you cross it is held together by the electromagnetic force between atoms. The food that feeds you is powered by the nuclear reactions of a star 50 million kilometers away. The phone in your hand is running a relativistic correction so that the blue dot on your screen knows which street you're standing on. Physics, all of it, quiet, constant, unremarked. We don't usually go looking for it. But sometimes, at the end of a long day when the lights are low and the world has gotten small and still, it finds you. This sense that the ordinary is threaded through with something extraordinary, that the things you take for granted rest on foundations that would have astonished anyone who lived even 100 years ago. Einstein is in your pocket. The satellites are awake above you. Your head is a little older than your feet. And wherever you are right now, whatever city, whatever country, whatever quiet room with its particular ceiling and its familiar sounds, the same physics is true. The same correction is running. The same equations that Einstein wrote in 1905 and 1915 in a patent office in Switzerland, before the world had aeroplanes that crossed oceans or satellites or atomic clocks or any of it. Those equations are describing right now the rate at which time is passing at your altitude in your gravitational position in your small corner of a very large and quietly astonishing universe. You don't have to understand all of it. You don't have to hold it all in your mind at once. You can let it go now. Let it settle like sediment in deep water, slow and peaceful and complete. The understanding doesn't have to be sharp and urgent. It can be soft. It can be the kind of knowing that lives in the back of the mind, not as an equation or a fact to be recalled, but as a feeling a quiet sense of depth, of layers beneath the ordinary, of a world that is genuinely and verifiably strange in ways that are also somehow beautiful. That's what I hope to give you tonight. Not just the numbers, though the numbers matter, and I hope they stay with you in some form, but the feeling underneath the numbers, the feeling of standing at the edge of something real and looking out at how far it goes. We started tonight with your head and your feet 33 centimetres apart, living in different times. We walked back through the engineering to the physics, through the physics to the experiments. The tower at Harvard in 1959, the aircraft flights in 1971, the rocket in 1976, through the experiments to the first navigation satellite with its on-off switch, waiting for the universe to answer. Through the switch to the equations, and through the equations back to a man in Bern, working at a patent office, thinking very carefully about light and time and gravity. And then we followed it forward again, through the orbiting constellation, through the ground station in Colorado, through the firmware in your phone, through the trilateration math running silently while you sleep, all the way to the blue dot on the map. And the blue dot is right, because Einstein was right. I'll mention, before we close, if you'd like to spend more quiet nights like this one, drifting through the strange and lovely machinery underneath ordinary things, a gentle like and a subscription helps this small channel keep going. Small creators like me really do rely on your support to keep making these. And if you have a moment to leave a comment, I'd love to know where in the world you're listening from tonight and what time it is in your corner of the dark. That's always my favorite thing to wake up to in the morning, a little map of everyone who spent a night like this with me. But that's for later. For now, let everything go. The satellites are still up there, moving steadily through the dark, their clocks ticking at exactly the rate Einstein predicted, their signals reaching down through the atmosphere to wherever you are. The master control station in Colorado is still watching. The correction is still running. And somewhere in the firmware of the phone that's probably on a table near you or tucked beside you in the blankets, the number 10. 22999543 megahertz is still part of the story of how you know where you are. You can sleep on that. Time is running a little faster at your head tonight, just as it always does, just as it was always going to. The universe is doing what it does as Einstein described it, as the experiments confirmed it, as the satellites verify it moment by moment in orbit, above you right now. It's a good thing to carry into sleep. Good night, kiddo. Grandpa'll leave the porch light on.